Today we will discuss about thermochemistry. Introduction. The chemical reactions are invariably accompanied by energy change which ordinarily appear in a form of evolution or absorption of a heat. Thermochemistry is a branch of physical chemistry which deals with the thermo or heat change caused by chemical reaction. The energy change that occur in a chemical reaction is largely due to a change of a bond energy. Such change of a potential energy that result from the breaking of a bond in a reactant and formation of a new bond in a product. We have studied in Unit 11 that every substance has a definite amount of energy known as intrinsic or internal energy E. Its extra value cannot be determined by the change in internal energy. Del E can be accurately measured experimentally. 2H2 plus oxygen give water 2 mole of hydrogen, 1 mole of oxygen give 2 mole of water. Del N is equal to 2 minus 3 is equal to minus 1. Qp is equal to Qv minus RT. Since in reaction involve only solid and liquid, del V is negligible. Qp is equal to Qv such that the enthalpy of a reaction at constant pressure is almost same as enthalpy of a reaction at a constant volume. Factor affecting heat of a reaction. These are some factors which affect the quantity of a heat evolved or absorbed during a physical or a chemical transformation. These factors are at constant pressure or at constant volume. Second, physical state of reactant and product. Third, amount of reactant and product. Fourth, temperature. Fifth, pressure. The physical state in a thermochemistry reaction are represented by symbol S or L. G and AQ for solid, liquid, gas and aqueous solution respectively. Consider a reaction. H2 plus half oxygen give water. Enthalpy is equal to minus 68.32 calorie. This reaction indicates that when 1 mole of a hydrogen reacts with 0.5 mole of oxygen, 1 mole of water is formed and 68.32 calorie of heat is evolved at constant pressure. If 2 mole of hydrogen are burned, the heat evolved would be 2 into 68.32 kilocalorie. This equation is not complete thermochemistry equation because it does not specify water is in the form of a stream or a liquid. This is the difference in the value of H if water is in the liquid or gas state as given below. H2 gas plus half oxygen gas give H2O2 liquid. Del H is equal to minus 68.32 kilocalorie. Hydrogen plus oxygen give water. Del H is equal to minus 57.80 if their water is in a gaseous phase. Enthalpy of a reaction or heat of a reaction. The enthalpy of a reaction is simply the amount of heat absorbed or evolved in the reaction. As we know that amount of heat absorbed or evolved at constant temperature and pressure is called enthalpy. Hence the amount of heat change during a reaction when internal energy of a reactant ER is greater than the internal energy of product EP. The difference in internal energy del E is released as heat energy. Del P is equal to E product minus E reactant. Such a reaction is called exothermic reaction if the internal energy of product is greater than internal energy of reactant. Heat is absorbed from the surrounding. Such a reaction is called endothermic reaction. The amount of heat released or absorbed in a chemical reaction is called the heat of a reaction. As we have discussed above, the energy change in a chemical reaction are largely due to breaking of existence bond between the atom or a formation of a new bond. Thus, thermochemistry provides useful information regarding bond energy. Heat of a reaction. Thermochemistry reactions are studied either at a constant volume or a constant pressure. The magnitude of a change observed under the two conditions of a different. The change in internal energy is the heat change accompanied a chemical reaction at constant volume because no external work is performed. But at constant pressure, there is a change in internal energy and work is also involved because of expansion or contraction. In the laboratory, most of the chemical reactions are carried out at a constant pressure rather than at constant volume. In order to study heat change for a reaction taking place at constant pressure and constant temperature, a new term enthalpy has been introduced. As we have studied in Unit 11, The enthalpy of a system is defined as a sum of the internal energy product of the volume and the pressure, that is H is equal to E plus PV, where H is the enthalpy, E is the internal energy, P pressure, V volume of the system. The term enthalpy is called H is called heat content. If internal energy enthalpy is also a state function and it does not possible to measure its absolute value. However, a change in enthalpy accompanying a process can be measured accurately and is given by the expression del E, del E is equal to H product minus H reactant HP minus HR. In this case, however, del Hp and del Hv such that Qp and Qv would be equal as there is no volume change involved. Now we take the following equation. C7H8 plus 9 oxygen gives 7 carbon dioxide plus water. In this case, Qp is equal to minus 9330 kilocalorie, Qv is equal to minus 298.8 kilocalorie. Relationship between enthalpy of a reaction at constant volume and at constant pressure. The quantities del H and del E are related to each other by the expression form equation 12.1 del H is equal to del E plus P del V, where del V is the change in volume that takes place in a given reaction. Since Qv is equal to del E and Qp is equal to del H, then Qp is equal to Qv plus P del V. For n mole of an ideal gas, Pv is equal to nRT. Suppose n1 and n2 represent the number of mole of a gaseous reactant and gaseous product, respectively, and suppose n2 is greater than n1, then increase in number of gaseous mole n2 minus n1 is equal to del Ng. Then P del V is equal to PV divided by N del Ng is equal to RT into del N. As PV is equal to nRT, P del V is equal to del Ng RT. Let us discuss, for example, dissociation of ammonia into nitrogen and oxygen. 2NHO3 give nitrogen and hydrogen. 2 mole of ammonia react with give 1 mole of nitrogen and 3 mole of hydrogen. Del Ng 4 minus 2 is equal to 2. Qp is equal to Qv plus 2RT. In the reaction involving combination of hydrogen and nitrogen, at constant pressure and temperature, the change in enthalpy del H will be equal to change in internal energy del E and the work done in expansion or contraction P del V. Hence, del H is equal to del E plus P del V. Therefore, while each change in a process is equal to its change in internal energy del E at constant volume, it gives at constant pressure the enthalpy change del H. Del E is equal to heat change at constant volume del H heat change at constant pressure. For reaction involving solid and liquid only, the change in a volume is very small and hence the term P del V is so small that it is neglected. For such reaction, del E is equal to del H. In case of gaseous, we have to specify whether the reaction is taking place at constant pressure or at constant volume. Because the value of a P del V is appreciable, most of such reactions are however studied at constant pressure and change in enthalpy del H is involved. Exothermic and endothermic reaction that give out heat such that when are accompanied by evolution of heat are called exothermic reaction. On the other hand, the reaction which are accompanied by absorption of heat are called endothermic reaction. Let us consider a general reaction at constant pressure. A plus B gives C plus D. Such enthalpy of A is HA, enthalpy of B is HB, enthalpy of C is HC, and enthalpy of D is HD. Then heat of reaction at constant pressure del H is equal to difference in enthalpy of a product and the reactant. Del Hc plus del Hd minus del Ha plus del Hb. The value of heat of a reaction del H may be 0, negative, positive. When del H is equal to 0, the enthalpy of reactant and product become the same. No heat is evolved or absorbed. In case of del H is negative, the sum of enthalpy of a product is less than that of a reactant and the difference in enthalpy is given out in the form of heat. Such reaction in which evolution of heat energy take place are called exothermic reaction. Del E2 minus del E1 is equal to del Cv into T2 minus T1. Similarly, heat of reaction at constant pressure is given by the relation del H is equal to H2 minus H1, where H2 and H1 are heat content or enthalpy of product and reactant respectively. Differentiating equation 12.5 with respect to temperature at constant pressure, we get this equation Cp2 minus Cp1 is equal to del Cp. Here Cp2 and Cp1 are the heat capacity of a product and reactant respectively. D del H is equal to del Cp dt. Integration the equation between time t1 and t2, we have del H2 minus del H1 is equal to integration t2 to t1 del Cp dt is equal to del Cp t2 minus t1. The relation 12.3, 12.4, 12.6, 12.7 were first derived by Kirchhoff and are called Kirchhoff equation. These equations are used to calculate heat of a reaction at a given temperature, provide heat of a reaction at some other temperature, and when the heat of capacity and product and reactant are known. Different type of heat of a reaction, enthalpy of a reaction. Heat of a formation, that change in enthalpy that take place when 1 mole of a compound is formed from its element is known as heat of a formation. It is noted by del HF. Heat of formation, for example, the heat of formation of a ferric oxide may be expressed as constant pressure, and constant temperature may also be called enthalpy change. Heat of a reaction may be defined as the amount of heat absorbed or evolved in a reaction when number of a mole of a reactant as represented by the balanced chemical equation change completely into product. It is very important to note that heat of a reaction vary with the change in temperature. Hence, we must mention the temperature at which the reaction is taking place. It is also convenient for a comparison to fix up some temperature as a standard or a reference. By thermodynamics convention, the state of a substance at 298 Kelvin and 1 atmospheric pressure is taken as its standard state. The heat change accompanied a reaction taking place at 298 Kelvin and 1 atmospheric pressure is called standard heat change or standard enthalpy change. It is denoted by del H naught. Variation of heat of a reaction with temperature. The heat of a reaction changes with the temperature of a gas due to variation in a specific heat. The equation represents the variation of heat of a reaction with temperature is known as Kirchhoff equation. At constant volume, the heat of reaction del H is given by the relation del E is equal to E2 minus E1, where E2 is the internal energy of a product and E1 is the internal energy of a reactant. Differentiating this equation with respect to temperature, keeping volume constant, we get del E by del T is equal to Cv. Here Cv2 is the heat capacity of product and Cv1 is the heat capacity of reactant. On integrating the above equation between the limit T1 to T2 and keeping in use that when temperature T1 heat of a reaction is del E1 and when temperature T2 heat of a reaction is del E2 is taken as minus 13.7 kilocalorie. The enthalpy of dissociation of acetic acid may be taken as 0.5 kilocalorie. The heat of dissociation of weak acid or weak base may be defined as change in enthalpy of a system when 1 mole of dissociation into ion. Heat of fusion. Heat of fusion is defined as heat change when 1 mole of a solid substance is converted into liquid state at its melting point. H2 solid to H2 liquid. Del H is equal to 1.43 kilocalorie. Here ice melt at 273 Kelvin and change into liquid water by absorbing 1.43 kilocalorie heat. It is found that greater the heat of fusion of a substance, higher the magnitude of intermolecular force. Heat of vaporization. The heat of vaporization is defined as change in enthalpy when 1 mole of a liquid is converted into vapor or a gaseous state at its boiling point. For example, 1 mole of water is converted into steam at 100 degrees Celsius or 373 degrees Kelvin. The heat absorbed is 9.71 kilocalorie, which is heat of vaporization of water. H2 liquid change into H2 gas. Water change into steam. Del H is equal to 9.71 kilocalorie. Heat of sublimation. In sublimation process, a solid change into a gaseous state without changing in liquid state. Sublimation occur at a temperature below the melting point of a solid. Heat of a sublimation is defined as enthalpy change when 1 mole of a solid is directly converted into gaseous state at a temperature below its melting point. For example, the heat of sublimation of iodine is 14.92 kilocalorie per mole. It can be represented as Fe plus S solid give FeS solid. Heat of formation is equal to minus 24 kilocalorie. This equation can be explained as 1 mole of a ferric iron react with 1 mole of sulfur in a solid form to form 1 mole of ferrous sulfate in a solid form, and 24 kilocalorie heat is evolved. The reaction becomes gaseous hydrogen and gaseous chlorine to form gaseous hydrochlorine is represented by equation. Hydrogen gas plus chlorine gas give HCl gas. Heat of enthalpy is minus 44 kilocalorie. This is equation means 1 mole of a gaseous hydrogen react until 1 mole of a gaseous chlorine to form 2 mole of a gaseous hydrogen chloride, and 44 kilocalorie heat is evolved. It may be noted in this case that 44 kilocalorie is not heat of a formation of HCl, because this amount of heat is evolved when 2 mole of hydrogen chloride are formed. The heat of formation of hydrogen chloride would be minus 44 by 2 is equal to minus 22 kilocalorie, and the equation can be written as half hydrogen plus half chlorine give HCl gas. Del H is equal to minus 22 kilocalorie. Standard heat of formation. The standard heat of formation del H naught F naught is the enthalpy change when 1 mole of a substance is formed from its element in a standard state. This is all substances are at 298 Kelvin and 1 atmospheric pressure. Heat of formation value may be exothermic or endothermic. Determination of enthalpy of a reaction. Enthalpy of reaction at 25 degrees Celsius can be determined if del HF naught of a reactant and a product involved in the reaction are known since del H naught is equal to del F H naught product minus del HF naught reactant. Del E2 minus del E1 is equal to del Cv into T2 minus T1. Similarly, heat of reaction at constant pressure is given by the relation del H is equal to H2 minus H1. Here, where H2 and H1 are heat content or enthalpy of a product and reactant respectively. Differential equation 12.5 with respect to temperature at constant pressure, we have Cp2 minus Cp1 is equal to del Cp, where Cp2 and Cp1 are the heat capacity of product and reactant respectively. Del H d del H is equal to C del Cp dt. Integrate the equation between temperature T1 to T2. Del H2 minus del H1 is equal to integration of del Cp dt T1 to T2. Del Cp into T2 minus T1, the relation 12.3, 12.4, 12.6, 12.7 were first derived by Kirchhoff and Kirchhoff equation. These equations are used to calculate heat of a reaction at a given temperature, provide heat of a reaction to some other temperature, and when the heat of capacity and product reactant are known. Different type of heat of a reaction, enthalpy of a reaction, heat of formation. The change in enthalpy that takes place 1 mole of a compound it formed from its element is known as heat of formation. It is denoted by heat del HF. For example, of heat of formation of ferric oxide may be expressed as the heat of a solution of an electrolyte may be due to energy change involved during insolation or some hydration formation as sulfuric acid. Usually, heat is absorbed when ions are turned apart from each other in the process of solution, and heat is evolved during hydration formation. Heat of a neutralization. The change in heat content of a system when 1 gram of equivalent of acid is neutralized by 1 gram equivalent of a base or vice versa. In dilute solution is known as heat of a neutralization. Following are some examples of heat of a neutralization. HCl plus NaOH give NaCl plus water. HNO3 plus aqueous solution plus NaOH aqueous solution give NaNO3 aqueous plus water. Del H is equal to minus 13.69 kilocalorie. Nitric acid plus KOH potassium hydroxide give KNO3 potassium nitrate plus water. Del H heat of enthalpy minus 13.87 kilocalorie. For this equation written above, it is observed that heat of neutralization of a strong acid and strong base is minus 13.7 kilocalorie. This can be explained with the help of a theory of ionization. If Ha and BOH represent a strong acid and strong base respectively, the equivalent amount of these is in a dilute solution be mixed. We have H positive plus aqueous plus A aqueous plus B aqueous plus OH aqueous give A aqueous plus B aqueous plus water. Del H heat of enthalpy minus 13.8 kilocalorie. Hence H positive aqueous plus OH aqueous give water liquid. Del H heat of enthalpy is equal to minus 13.7 kilocalorie. This the heat of neutralization of an acid and base is merely heat of formation of water with from hydrogen and hydroxyl ion. If, however, the acid or alkali is weak, the enthalpy of neutralization is different because the reaction now involves dissociation of a weak acid and weak alkali as well as neutralization of acidic acid with sodium hydroxide, for example, involving the dissociation of acid as well as useful neutralization of H positive and OH ion as represented below. Acetic acid broken into acetic ion and H positive ion. H positive plus OH aqueous give water. As H positive ion neutralized by OH ion furnaces by completely dissociation of a sodium hydroxide. More H positive ion are formed by dissociation of acetic acid, destabilize the equilibrium. Thus, both the reaction proceed side by side till acetic acid is completely neutralized. The enthalpy of a neutralization of weak acid by sodium hydroxide has been found to be minus 13.2 kilocalories since the average value of combination of H positive and OH negative I2 solid change into I2 gas. Del H 14.92 kilocalorie. Heat of a transition. The change in enthalpy when one mole of an element from one allotrope form to another is called heat of a transition. For example, transition of a diamond into amphoteric carbon be represented as a carbon diamond change into carbon amphors and the heat of enthalpy minus 3.3 kilocalories. Similarly, phosphorus white change into phosphorus red and enthalpy of heat change into 1.028 kilocalorie. Hess's law of a constant heat summation. The energy change accompanied chemically process are governed by a general principle known as Hess's law. This law states that the amount of heat evolved or absorbed in the process in the same way that the process takes place in two or more different ways in one step or in several steps. Let us suppose that a substance A can be changed into Z respectively. Del A change into Z plus Q1. Del H1 change is equal to minus Q1, where Q1 is the heat involved in the direction change. When the same change in brought about a stage, A change into B plus Q1, B change into C plus Q2, C change into Z plus Q3. Del H2 is equal to minus Q1, del H2 is equal to minus Q2, del H3 is equal to minus Q3. The total evolution of heat Q1 plus Q2 plus Q3 is equal to Q2. According to Hess's law, Q1 is equal to Q2. If it is not so, let Q2 greater than Q1, then be transforming A to Z those state and transforming directly back to A, there would be gain of a heat energy Q2 minus Q1. By repeating the process again and again, unlimited heat energy will be developed in isolated system. This goes against the first law of thermodynamics, hence Q1 must be equal to Q2. Example of Hess's burning of a carbon to carbon dioxide. Carbon can be burned to carbon dioxide directly, or it may first change to carbon monoxide, which may then it oxide to carbon dioxide. First way, Carbon solid plus oxygen give carbon dioxide. Del H, heat of enthalpy minus 94.05 kilocalorie. Second way, carbon solid plus half oxygen give carbon dioxide gas. Del H, heat of enthalpy 26.42 kilocalorie. Overall, carbon plus oxygen gas give carbon dioxide heat of enthalpy minus 94.1 kilocalorie. It is shown in figure 12.2. Application of Hess's law. First, calculation of enthalpy of a reaction. With the help of a Hess's law, it is possible to calculate enthalpy of a many reaction which cannot be determined experimentally. For example, it is extremely different to measure the heat evolved when carbon burnt in oxygen to form carbon monoxide. Carbon plus oxygen give carbon monoxide. For the Hess's law, it is known that the heat evolved in the combustion of a 1 mole carbon dioxide is same wise whether the reaction takes place in single step as carbon solid plus oxygen give carbon dioxide. Heat of a change is minus 94.05. Where del H is positive means there by the enthalpy or heat content of a product is more than of a reactant and equivalent heat is absorbed by the system for a surrounding. Such reactions which are accompanied by absorption of heat are called endothermic reaction. Thus, for the endothermic reaction, Hp greater than Hr and del H positive, and for endothermic reaction, less than Hr and del H negative. In chemistry, it is customary to represent thermochemistry change as for exothermic reaction HCl plus NaOH give NaCl plus water plus 13,700 calorie. For endothermic reaction N2 plus O5 to NaOH minus 42000 calorie, 42,000 kilocalorie. That is, in case of heat evolution, the quantity of heat evolved is written with the product with a positive sign. In heat absorbed, the quantity of heat is written with the product with a negative sign. Hence, that is, in case heat evolution, the quantity of heat evolved is written with the product with the positive sign. In heat absorbed, the quantity of heat is written with the product with the negative sign. Hence, 13,700 calories is equal to heat of neutralization of HCl plus NaOH minus heat of neutralization of NaCl plus water. And minus 42,000 calories is equal to heat of neutralization of Na2 plus O2 minus H to NO. In thermochemistry, the attention is concerned on a system. In exothermic change, heat content or energy content of system would diminish. In endothermic, these would increase. Hence, we write HCl plus NaOH give NaCl plus water. Heat of change in enthalpy is equal to minus 13.700 calorie. Nitrogen plus oxygen give 2NO. Heat of enthalpy 42,000 calories. By convention, del HF naught value of element in their standard state are taken as 0. This concept has been shown in the following equation. Example, calculate del H naught for equation CO2 plus H2 gas gives CO plus water. Give that del HF naught for CO2 gas and carbon monoxide and water are minus 393.5 minus 111.31 and minus 241.80 kilojoule more per liter respectively. Del H naught is equal to del HF naught minus del HF naught reactant minus the answer is 40.4 kilojoule. Heat of a combustion of a substance is change in enthalpy when 1 mole of a substance is completely burnt in excess of oxygen. Heat of combustion is denoted by del Hc. The combustion of a methane as shown. Methane plus oxygen give carbon dioxide plus water. Heat of a combustion minus 87.78 kilojoule. Combustion of hydrogen similarly can be represented as hydrogen plus oxygen give water. Heat of a combustion minus 285.29 kilojoule. Now let us consider the following chemical equation. Carbon plus half oxygen give carbon dioxide and heat of enthalpy minus 26 kilocalorie. It may be noted that minus 94.3 calories is the heat of combustion of a carbon, as combustion is the complete in equation. In this first case, carbon has been converted into carbon monoxide and by no means completely oxide. It can be further oxidized to carbon dioxide. Use of heat of a combustion. Calculation of a heat of a formation. The formation of a combustion of an organic compound can be easily determined. These are employed to calculate their heat of formation, or in two steps, as carbon plus oxygen give carbon dioxide and heat of enthalpy is x kilojoule या kilocalorie. Carbon monoxide plus oxygen give carbon dioxide and heat of enthalpy is y kilocalorie. Although x, the heat change involved in combustion of carbon monoxide, can not be determined easily, y, the heat involved in the combustion of carbon monoxide to give carbon dioxide, can be measured and has been found to be minus 67.61 kilocalorie according to Hess's law. X plus y is equal to minus 94.05 kilocalorie. Thus, del H heat of a combustion of a carbon to get carbon monoxide is minus 26.34 kilocalorie. Second, determination of enthalpy change of a slow reaction. Hess's law is extremely useful in determining enthalpy change of those reactions which take place extremely slow. For example, the transformation of a rhombic sulfur into monoclinic sulfur is so slowly that direct measurement of enthalpy change is not possible, but the enthalpy of combustion of rhombic sulfur are known to be respectively such that S rhombic plus sulfur rhombic plus oxygen give SO2, heat of enthalpy minus 297.5 kilojoule. Sulfur monoclinic plus oxygen give SO2 gas, heat of enthalpy 300 kilojoule. Subtract first from a second, rearranging we get C monoclinic sulfur monoclinic into sulfur rhombic give del H is equal to minus 225 kilojoule या 2.5 kilojoule. Thus, transformation of 1 mole of rhombic sulfur into monoclinic sulfur is accompanied by absorption of a kilojoule of heat. Calculation of enthalpy of formation. The enthalpy of formation of a compound can be calculated by the application of Hess's law when it is not possible to determine these experimentally. For example, it is impossible to determine experimentally the enthalpy of formation of a benzene from its element carbon and hydrogen. However, it can be calculated from the enthalpy of combustion of a benzene and the enthalpy of formation of water and carbon dioxide. The solution is carried out in a term two steps. Add equation 4 and 6 and subtract from equation 5. We have carbon plus hydrogen give methane and heat of enthalpy 1660.7 kilojoule. It follows from above equation that minus 1660.7 kilojoule of energy is required to break 4 mole of carbon and hydrogen bond in methane. Therefore, the average bond energy per mole of a carbon hydrogen bond is 1660.7 by 4 is equal to 415.2 kilojoule. This is also enthalpy of formation of a carbon and hydrogen bond. Summarization. In this unit we have studied different definition association with thermochemistry. As we know, thermochemistry is the study of energy change involved in a chemical reaction. This study is very useful in determining enthalpy change in various reactions. Kirchhoff equation is very useful in calculating change of an enthalpy with temperature. Hess's law and bond energy calculated are utilized for various transformation. And there are some questions which will solve itself. Bond energy. Bond energy for any particular type of a bond in a compound may be defined as the average amount of energy required to dissociation 1 mole Avogadro number of a bond of that type bond is in a compound. This is also called the enthalpy for formation of a bond. Thus, the bond of a hydrogen bond in the energy required to break all bonds in a 1 mole of a gas. It is expressed in a kilocalorie per mole or a kilojoule per mole. For example, bond energy of hydrogen bond is 433 kilojoule per mole or 103.58 kilocalorie per mole. Bond energy of some common bond are given below. Suppose we have to determine the enthalpy of formation of a carbon hydrogen bond in methane. We should know that enthalpy of formation of a methane. This has been calculated from the enthalpy of combustion of a methane to be minus 74.9 kilojoule. Thus, carbon plus oxygen give methane enthalpy of heat, या enthalpy of combustion is equal to minus 74.9 kilojoule. Multiplying equation first by 2, we have 2 hydrogen plus 2 hydrogen gas give 4 hydrogen. Del H is equal to 866.2 kilojoule. There is some examples for enthalpy of heat. Second, calorific value of a food and fuel. The amount of heat produced when 1 gram of a substance is completely burned is known as calorific value of a food or a fuel effectively. It is expressed in kilo per gram, calorie per gram, or a kilocalorie per gram, or a kilojoule per gram. Methane has better fuel efficient than ethane as it produces more heat per gas gram. It can be explained by comparing heat of combustion of methane and ethane. Heat of combustion of methane is minus 890.3 kilojoule and the ethane minus 1559.7 kilojoule. Methane plus oxygen give carbon dioxide plus water. Heat of enthalpy, heat of calorific value is minus 890.3 kilojoule. Ethane plus oxygen give carbon dioxide plus water. The heat of enthalpy is minus 1559.7 kilojoule. For methane, heat produced per gram is minus 54.6 kilojoule per gram. For ethane, heat produced per gram 51.90 kilojoule per gram. Molecular weight of methane is 16 and ethane is 13. Thus, methane has a better fuel efficiency than ethane as it produces more heat per gas gram. Deciding constitution. Heat of a combustion of organic compound is to be a large extent an additive property as shown by the fact that in a homologous series the difference between the heat of a combustion of successive member is nearly constant and it's equal to 158 calorie. Constant corresponding to the heat of a combustion of various atom and linkage has been worked out. The heat of a combustion of an organic substance can be calculated from the probability structure formula by adding up the value of a constant corresponding to the atom and the linkage involved therein. If the value of obtained come out of to be the same as the experimental value of a heat of combustion of the compound, the assumed formula must be correct. Heat of a solution. When a substance is dissolved in a solvent, heat change are usually observed when reaction take place in a solution. Heat of a solution of a reactant and product has been taken into account. The heat of a solution is defined as the change in enthalpy when 1 mole of a substance dissolved in a specific quantity of a solvent at a given temperature. If the substance is dissolved in a solvent, certain amount of heat is evolved or absorbed. If the solution is further diluted, there will be again be change in enthalpy. If we go on a dilution, the solution a stage will come when further dilution produce no thermal effect. This is called the state of infinite dilution. To avoid the quantity of a solvent, we have to incorporate the idea of infinite dissolution in the definition, which may be stated as the heat of a solution is the change in enthalpy when 1 mole of substance is dissolved in a solvent so that further dilution does not give any change in enthalpy. Thus, KCl plus water give KCl equals del H is equal to minus 4.4 kilocalorie. Magnesium sulfate plus water give magnesium sulfate aqueous. Heat of enthalpy 20.28 kilocalorie. The heat of solution of electrolyte may due to energy change involved during isolation or some hydrated formation as sulfuric acid. Usually heat is absorbed when ions are turned apart from each other in the process of a solution, and heat is evolved during the hydration formation. Heat of a neutralization, the change in heat content of a system when 1 mole of a equivalent of an acid is neutralized by 1 gram equivalent of base, or vice versa, in a dilution solution is known as heat of a neutralization. Following are some example of heat of a neutralization. For this equation written above, it is observed that heat of a neutralization of a strong acid and strong base is minus 13.7 kilocalorie. This can be explained with the help of a theory of ionization. If Ha and BOH represent any strong acid and strong base, and the equivalent amount of these is a dilution solution be mixed with, we have a H positive aqueous plus A aqueous plus B aqueous plus OH aqueous. Change into A aqueous plus B aqueous plus water, del H minus 13.7 kilocalorie. Hence, H positive aqueous plus OH negative change into HCl liquid. Del H is equal to minus 13.7 kilocalorie. Thus, the heat of neutralization of acid and a base is merely heat of formation of water from hydrogen and hydroxyl ion. If, however, or the acid or alkali is weak, the enthalpy of neutralization is different, because the reaction now involves dissociation of weak acid or a weak alkali as well as neutralization of acetic acid and sodium hydroxide. For example, involved in the dissociation of the acid as well as the usual neutralization of H positive and OH negative ion as represented below. As H positive ion are neutralized by OH negative ion furnished by the completed dissociation sodium hydroxide, more H positive ion are formed by dissociation of acetic acid to re-establish by the equilibrium. Thus, both the reaction proceed side by side till acetic acid is completely neutralized. The enthalpy of neutralization of acetic acid and sodium hydroxide has been found to be minus 13.2 kilocalorie. Since the average value of combustion of H positive and OH negative ion is taken as 13.7 kilocalorie, the enthalpy of dissociation of acetic acid may be taken as 0.5 calorie. Thank you. The chapter is complete.